data recorded. And we aim at estimating some parameters theta or some features theta from them. And in order to do that, what we are going to do is to solve some optimization problem in order to minimize some cost function f, where the cost function corresponds to the model that we are considering for the data, and the data themselves x and the parameters theta might possess a structure, so set of constraints and invariances. So their domains x and m are in fact manifolds. So to deal with this problem, we aim at using some geometry. So geometry, we have, I will go in details a bit later, but we have a nonlinear space M where we can we have some points and we can define some curves and some metric and some distances and stuff like that. And it's quite useful to deal with problems where data or parameters have some specific structure. And it's quite powerful because we can use geometry both for modeling, optimization, and performance analysis. So for modeling, in fact, we can consider the structure of the data or the parameters in order to define appropriate cost function. So it will be our first example today. I will talk about this for blind source separation. And we can also use it to solve the problem, so to find the parameters theta of interest by using Riemannian optimization. And the advantage is that it naturally takes into account the structure of the variable that we seek. And finally, it will be the last example I will present. It's very useful for performance analysis, where we can define some performance bounds, some intrinsic covariance intrinsic Cramér-Rao bound, and define some geometrical error measures. Okay, so here the outline. So first I will talk a bit about Riemannian geometry and optimization to introduce what it really is. So in particular, I won't present optimization in the examples below, so it will be the only introduction I will give. And then I will show you two examples. So the first for approximate diagonalization for blind source separation, which is an example for the use of geometry in modeling cost function. And the other one, intrinsic Cramér-Rao bound for low-rank structured elliptical models, where we have some performance analysis use of geometry. And finally, I will finish with some conclusions and perspectives. Okay, so first, Riemannian geometry. The idea is that we deal with a manifold, and a manifold is some space that is around each of its point theta. In fact, it's similar to a linear space. So basically, we can find a map around each point, which maps the points of the manifold onto a vectorial space. And from there, we can define some curves on the manifold, which are from the space of real numbers to the manifold. Such that we have some starting points here, and we can define the derivative in a classical way of the curve here. And that allows us to define the tangent space of the manifold, by taking, in fact, all the curves that go through a point and taking their derivatives at this point, and this defines the tangent space. So things get really interesting when we then define a Riemannian metric on the manifold. So it's a bilinear map from tangent spaces onto real numbers. It's an inner product. And what it really allows to do is to define length of tangent vectors and also the relative positions of tangent vectors between them. So we have an idea of where is a tangent vector C from a tangent vector eta by considering the angle, for instance. And the first, we can do a lot of things with a Riemannian metric, and the first thing and most important maybe is the geodesics. So geodesics generalize the concept of straight lines to manifold, and it's basically the idea of straight lines is curves on the manifold with no acceleration. So no acceleration, we have this differential equation here, and I won't talk more about the operator of second derivatives here, but just know that it depends on the structure of the manifold and on the choice of the Riemannian metric. So then from there we can define Riemannian distance, and the Riemannian distance is just defined by measuring the length of the geodesics between 2 points here. Okay, so from there, another thing that is important is Riemannian optimization, where we aim at finding the minimizer on the manifold M of some cost function. And so for that, there has been a whole framework for optimization that has been developed, and that you can find, for example, in this reference here. And the idea is that we have a cost function and we are aiming at finding a descent direction. So for that, descent direction is given by some tangent vector that allows to have a negative directional derivative of the cost function, so that allows to have a decrease in the function here. And to find such a direction, a very useful tool is the gradient, which is defined thanks to the Riemannian metric here. And we have this definition of the gradient here that generalizes the definition on Euclidean spaces. Okay, so from there, in fact, we can define a Riemannian optimization iterative procedure by given some point. The first step is to find a descent direction. So, for example, we can take the opposite of the gradients, but we can also take some more specific other the things such a Newton iteration or things like that. From this descent direction, then we are going to need to find the new corresponding points on the manifold, and for that we use a retraction of the tangent vector xi onto M, which gives another point. And as for any optimization algorithm, the goal is to reiterate the procedure until we find some critical point for which the gradient is small enough. So the very simple example of an optimization algorithm is the gradient descent, where the descent direction is taken by the opposite of the gradient multiplied by some step size ti, which can be computed with a line search, for instance. Okay, so it will be all on the theoretical parts. And now I'm going to talk to you about approximate joint diagonalization for blind source separation. So the problem of approximate joint diagonalization is that we have a set of positive definite matrices, and we aim at finding a joint diagonalizer B of these matrices that is a matrix B such that the transformed matrix B CK B transpose are as much diagonal as possible. And in fact, by as much diagonal as possible, we mean that the matrix B should minimize some criterion of the diagonality of the matrices CK. Okay. So that's the main application is blind source separation. And for instance, when we have some linear mixing of some observation X, so the observation X that we have are obtained by mixing some source S by matrix A. And in fact, we aim at finding so B as a joint diagonalizer of some covariance matrices of the data X in order to retrieve the original sources in B extra X. And it's, for instance, used in different engineering fields, and for instance in electroencephalography, where you have some sources which are some dipoles, some electrical activity in the brain that goes to the scalp through the brain, the skull, the scalp, and it mixes while it propagates to the different sensors, and we are in this context here. So we'll see that later at the end. Okay, so for approximate joint diagonalization, in fact, the thing is that we can adopt some geometrical modeling of the problem, and the fact to diagonalize the matrices CK with B as much as possible can be seen as the goal is to get the matrices CK as close as possible to the sets of diagonal positive definite matrices. And we can see the diagonality measure of the transform matrix BCK B transpose as the relative position with respect to the set of diagonal matrices. So what we proposed in this case is to have a geometrical model. And for that, the appropriate criteria are, for instance, the sum of the divergences between the matrices BCK B transpose and some target diagonal matrix on the set of positive definite matrices. And so this criterion, such a criterion, has two parameters: the choice of the divergence on the set of positive definite matrices, which will determine how we are going to get to the set of diagonal positive definite matrices, and the choice of the target diagonal matrices, which determines where on the set of diagonal matrices we are going to go. Okay, so once we have chosen some divergence D, there is a natural choice for the target diagonal matrices, which is given by the projection according to D of the transform matrices onto the set of diagonal matrices. Okay. So, in fact, in this work, we have considered several divergences, and the nice thing with this modelization is that, firstly, we find the usual criteria used for approximate joint diagonalization. So, for instance, the least square criterion is obtained by considering the Euclidean distance, and with for which the closest diagonal matrix to a matrix C is given by taking its diagonal parts. And also we find the log likelihood criterion by considering the left Kullback-Leibler divergence. So here again we have the closest diagonal matrix as the diagonal part of matrix C. But we can also find new and define new criteria for approximate joint diagonalization. For instance, just by taking the Kullback-Leibler divergence the other way around, we have a right measure. And in this case, and in any of the following cases, the closest diagonal matrix is different from the usual ones. And here it's so the inverse of the diagonal part of the inverse of the matrix. And if we take a symmetrized version of the Kullback-Leibler measure, then we have the geometrical mean of above matrices, diagonal matrices. Okay, so we have taken these into account, but also we have considered the natural Riemannian distance on the set of positive definite matrices, and so this corresponds to the Fisher distance of of the Gaussian distribution. So that's why it's quite interesting in our case. And also we have considered the log Euclidean distance, which is also related to Riemannian geometry. And one way to look at it is to see that it's a linearization of the natural Riemannian distance around the identity matrix. And another distance is the Batach area distance, which is very interesting because it has very similar properties as the Riemannian distance, but it is cheaper to compute, and it is also more stable from a numerical point of view. And finally, the last distance we considered is the Wasserstein one, which is closely related to optimal transport, and which has attracted some attentions lately. So okay, so from there I will show you directly some numerical experiments. So the first experiment we did with this criteria is on simulated data, and we simulated some sets of positive definite matrices according to this model. So we have some target matrices, the mixing matrix here, and some added noise with a signal to noise ratio parameter here. And to measure the performance of the recovery, we used the classical Moreau-Amari criterion, which measures the degree of similarity of BA with a matrix of the form P sigma, where P is a permutation matrix and sigma is a non-singular diagonal matrix, because in that case, if BA is equal to to a matrix of this form, then we have perfect recovery. And okay, so and then we used some optimization algorithm to find B with all the described criteria. So here on this simulated data, we have the Morat-Marie criterion, and so the lowest is the value here, the better is the performance, and also so from left to right we have increasing values of SNR. So here it's very easier. And what we plotted is the medians and the first and ninth deciles. So what we can learn from these results here is that we have mainly two groups of divergences. So we have the Frobenius, the Euclidean distance, and the Wasserstein distance here, which are performing poorly at low SNR, but which are performing quite well at high SNR. And we have all the others distance here that are quite have the same behavior for any values of the SNR. And in particular, we have the right Kullback-Leibler measures that performs very well on this data. And so, but for the Frobenius and Wasserstein distances, so it has very good performance here. We have the best performance at high SNR, but at low SNR, it degrades a lot. So it's not very strong measures, and depending on the conditions, it's not a good choice. Okay, so then the second experiment is on electroencephalographic data, where we have considered some SSV-EP data. So the idea behind data is using a fact of the brain. So if you take some light and you make it blink at a certain frequency, in fact, at the back of the brain, there will be some electrical activity that goes at the same frequency as the blinking of the lights. So here we have put some electrodes on some people, and we have considered 4 different experimental states. So different frequencies for the blinking of the light, so 13 Hertz, 17 and 21, and some rest condition as well. So here you have the Fourier spectra, so the power of the spectra, and you can see that we observe in the different conditions some peak at the at the corresponding frequency, and also here we have some signal around 10 Hertz, and this is some alpha waves which correspond to a normal activity of the visual cortex. And we have some noise, and you can see that the peaks are on most electrodes, and as well the alpha waves are also on different electrodes. Okay, so what we did here is to compute also some co-spectra of the matrices and apply the approximate joint diagonalization algorithms, and we obtained 2 sources. So the 2 sources of interest, the one corresponding to the SSVP activity of the brain, and you can see basically that it removed quite a lot of noise, and we clearly have the 3 peaks here. And we also obtain the alpha wave source here, which is active in all conditions. And to compare the different methods, we define some performance measure, which shows how the source corresponding to the SSVP activity is discriminating. So we took the ratio between the power at the frequency of interest and the total power of the source in each condition. And one thing that is important to notice here is that, and it's normal from a physiological point of view, it's a known fact, is that when the frequency increases, the power of the source decreases. So the signal to noise ratio of the SSVP source decreases as well. And what we can see on the results is that we also have the two groups of the simulated data. So all the divergences here, except for the least square criterion and the one based on the Wasserstein distance. And for these two, as before, they perform well for a good signal to noise ratio, but when it comes to the smaller signal to noise ratio, they perform significantly less than the other divergences. And all the other divergences have the same performance. Okay, so here it is for this example, and now I will go on to performance analysis example for the intrinsic Cramér-Rao bound for low-rank structure elliptical models. So first, so in this context, we again have some data that follow some law parameterized by theta, which belongs to a manifold, and we have the log likelihood Lx here for this law. And again, given the data, the estimation problem is to find theta hat, which is the minimizer of the negative of the log likelihood. And in this case, to find the optimal performance, we can use Cramér-Rao bound of unbiased estimators. And we have this kind of inequality here, where if we take the covariance error of theta and theta hat, we have a lower bound, which is given by the Fisher information matrix. And we can also take the trace of this inequality to have a bound of the mean square error in the classical case. So for this bound, in fact, in the classical case, the error is given by the Frobenius distance, so the least square distance between theta and its estimator, and the Fisher information matrix is given by this formula, so by taking the second derivative of the log likelihood. But so in the classical case, it doesn't take into account the constraints or the invariances of the model that we can have. And for instance, if we consider low-rank covariance matrices, there is quite a structure to take into account. So what we can do is generalize these classical results to a Riemannian manifold M, And in this case, so the error measure can be defined by taking the Riemannian distance on M between the parameter theta and its estimates. And so the Riemannian distance, which is associated to the Riemannian metric that we chose. And in that case, we have this inequality by taking the Fisher information matrix as defined as here. And here we have the Fisher metric, which is defined again with some second order derivative of the log likelihood. And the terms EI and EJ here are elements from the orthonormal basis of the tangent space of M at theta, which is associated to the chosen metric. And one thing that is quite interesting is that this bound allows to exhibit some different properties. For instance, for covariance matrices and stuff. Okay, so now in this work, we are interested in elliptical distributions and in low-rank structured covariance matrix. So in that case, the data X here are parameterized by some covariance matrix R, which is in the set of positive definite matrices. And we have this log likelihood here, which is parameterized by density generator G, which is a strictly positive function. And for example, in the Gaussian case, this is equal to that. And such this family of distribution also takes into account generalized Gaussian distribution, studente distribution, K distribution, and a lot of very interesting distributions, especially when we have outliers in the data and things like that. And so on the set of positive definite matrices, the Fisher metric of the elliptical distributions is now well known and is given by this expression here, where we have the natural. This here it corresponds to the Gaussian. So for the Gaussian case, alpha is equal to 1 and beta is equal to 0. And so this term here tends to show non-Gaussianity. And for that also, we are considering a model where R, the covariance matrix, has a low-rank structure. So we have R, the structure is that R is equal to the identity matrix plus some matrix H, where H is in the set of positive semi-definite matrices of rank K. So the size is P by P and the rank is K. And the geometry of this space here is quite complicated, and there have been quite a few work on that. So there are different possibilities, but there isn't one geometry that is ideal. So in this work, we will consider the geometry that arises from the SVD decomposition. So any matrix H of rank K can be decomposed like that, where U is an orthogonal rectangular matrices of dimension P by K, and sigma is diagonal matrix of size K by K. And in fact, if we do that, the decomposition is non-unique, and we have a problem with permutation matrices. So what we do is that we consider more general decomposition, and we allow sigma to be any positive definite matrix. And when we do that, so we have an invariance of this decomposition. So for any unitary matrix O, we have the equality between the decomposition with U and sigma and the decomposition with UO and OH sigma O. So what this means is that the set of positive semi-definite matrices of rank K is isomorphic to a quotient and to the quotient which is given by M here, where in fact the point of the quotient, one point of the quotient is a whole equivalence class of the product manifold here. And we have to take that into account when we study geometry. So what we can do to study the geometry of the quotient is to consider the tangent space of the M bar, which is the full manifold, and we will be able to characterize the tangent space of the quotient manifold by taking a subspace of this tangent space of the whole manifold. So the tangent space here is given by this, and we choose this metric here on the manifold. So I won't go too much into detail, but this one here on above is the metric related to the component U, and the one on the bottom is related to the component sigma, where we chose to have alpha and beta to have something that is similar to the Fisher metric of elliptical distributions here. And in fact, so the tangent space then can be decomposed into two complementary space. So the vertical space here, which corresponds to the tangent space of the equivalence class in the whole manifold. And in fact, we can then have a good representation of the tangent space of the quotient manifold by taking its orthogonal complements in the tangent space, and it's the horizontal space, which is given here. So you have some formulas here if you are interested. And the problem here with this geometry is that the corresponding Riemannian distance is not known. So the geometry of the quotient is quite complicated, and we are not able to retrieve this geometrical tool, so the distance. And so what we have to do is to go beyond Riemannian geometry and to find an alternative error measure. And to do so, what we do is that we choose an alternative horizontal space, which is given here. And the idea is that it's still complementary to the vertical space, but it is no longer orthogonal. And so what the consequences are that it will induce curves onto the quotient manifold, and it will in particular induce a divergence, which is given here, onto the quotient manifold, but this divergence is not a distance, and it's not it does not correspond to the Riemannian distance. And in fact, if we look at the divergence, the interesting thing is that we have the component here which is related to U, and it corresponds to the distance on the Grassmann manifold. And here we have some distance which corresponds to the Fisher distance for elliptical distributions on the set of positive definite matrices of size K. So we choose to define our error with this divergence, which comes from this alternative horizontal space. And to find a performance bound that is adapted to this error, so this divergence here, we can define, in fact, the alternative Fisher information matrix F here, where the elements here of the Fisher matrix. So here we have the Fisher information metric on of the elliptical distributions on the whole manifold, and here the EI and EJ are corresponding to the orthonormal basis of our alternative horizontal space according to the chosen metric on M bar. So it's given by these formulas here. And finally, so the last thing that we need is the Fisher metric of elliptical distributions on the manifold of interest. And so the log likelihood here is given by the log likelihood of positive definite matrices with this function of passage, where the phi bar is given by our formula here, and its directional derivative in direction of tangent vector c is given by this formula. And in fact, the nice thing is that the Fisher metric onto M bar is obtained by taking the Fisher information metric on the set of positive definite matrices at our transform point here, and with directional derivatives of the diffeomorphism here. So yes, and we know the Fisher information matrix of on positive definite matrices because it's been found in the literature before. And that's enough. And now we can go to numerical illustrations where we have done on simulated data. So the covariance matrix R here is simulated with according to this model. So we have the identity matrix, and then we have some random orthogonal matrix. We have a random diagonal matrix also, and we control the conditioning of this diagonal matrix. So it is equal to C, and we chose C equal 20 here. And the trace has been normalized as well. And we have also a three parameter sigma, which controlled the degree of low rank of the whole matrix R. And we chose to take sigma equal to 50 here. And for the data, we have simulated 500 Monte Carlo sets of n random samples, and we have considered two cases, so both in the t distribution. So some sets were equal to d t distribution with d equal to 3 degrees of freedom, so very non-Gaussian data, and d equal 100 degrees of freedom, so almost Gaussian. And we add these results here. So in dash here you have in both cases, so the bound, the Cramér-Rao bound that we have defined, and then you have several methods. So here in brown it is the projected SCM. So we compute the sample covariance matrix, and then we project it onto the set of low rank matrices. So as expected, it doesn't perform very well when the data are non-Gaussian, but it's the best estimator when the data are almost Gaussians. And then we have some Riemannian optimization algorithms, minimizing the log likelihood in the case of elliptical distribution. And we have, so here, oh no, it's Tyler, sorry, it's not the log likelihood, it's a Tyler estimator with the Riemannian optimization. And here we have gradient descent, Riemannian gradient descent, and here we have a Riemannian trust region. So here it's a first order method, and here it's a second order method. And what we see is that the second order method, as soon as we have as much data, are we close to have as much data as the size of the matrices, then it doesn't work anymore in both cases. But it performs well when we have a lot of data. And on the other hand, with the first order method, so with the gradient descent, it performs well when we have few data, even when we have fewer data than the size of the matrix, but still when it's we have more data than the rank of the matrices, and also here in the Gaussian way. But when we have a lot of data, it doesn't perform as well. Okay, so that's it for this illustration, and I will go to conclusions and perspectives. So in fact, so Riemannian geometry, it's quite a powerful tool for signal processing and machine learning, because it fully exploits the structure of the data and parameters. So it fully embeds the different constraints and invariants of the model. And lately, studying the structure is very much used in our communities. And also, one real advantage of the Riemannian geometry framework is that it's quite complete, because you can do modeling, optimization, and performance analysis. And also it allows a lot of modularity, because it separates these three aspects. So you can do some modeling and then do some optimization. And if you want to change some part of the optimization, you don't have to do anything for the modeling. And also the same goes the other way around. If you want to change some modeling, then you can still use the same optimization tools. So it's quite modular. And and then the question is when to use Riemannian geometry in optimization. So it's very useful when data or parameters have a structure. And also when there is a metric that is particularly interesting for the model, for example, the Fisher information metric in information theory. And on the other end, as we have seen for the low-rank structure matrices, one big issue is that for some manifolds, the geometry is complicated to fully characterize. So some elements, such as the Riemannian distance, for example, can be hard to find. But in that case, as we have seen, we can go beyond Riemannian geometry to provide geometrical objects that we can fully characterize and use in practice. So that's it for my presentation. Thank you for your attention, and we can go to questions.